Everybody, today we're going to talk about solving equations using visual models. So please make sure that you have that as your title to your notes. You have the essential question right after that. And the essential question today is, why do you do the same to both sides when solving an equation? In your explanation, I would like you to talk about the scale, hanger model, or tape diagram. You don't have to draw it, but you do have to talk about it. So that means you're going to do some drawing today in your notes. We're going to talk about 3 different models. I would like you to draw all 3 models in your notes. When you're solving a problem in the future, I will not force you as to which model you need to draw, but you do need to know about all 3 models. So there should be at least one example of each of those models in your notes. Okay? For your exercise today, you're just working on solving equations from visual models. And you should have your essential question answer at the end of your notes when you are done. This is a good time to remind you that since you're watching this video at home, please take advantage of the pause and rewind buttons. If you need to slow it down or rewind on what I just said, and fast forward if you feel like you got it, but just be sure that you're not missing out on anything important. Okay, so we're going to get started then. We're going to start with talking about solving equations from visual models, and this one right here is, as you can tell, the scale model. And you might want to pause the recording just to jot this down, this reminder. Remember, for equations, the left and right side are equivalent. On the scale, that means they weigh the same on both sides. And you make sure you write that down as I remember to label this as a scale model. Okay, so like I just said, for equations, if you remember, left side and right side have to be equivalent. So if we were to put those numbers and those variables, if we pretend we put them on a scale, like the one I've drawn here, remember that a scale, for scales to work, they have to show that both sides are equivalent, or else one side is going to be lopsided. And remember, on equations, there is the equal sign, right? So equal sign also shows us that the left side has to be equal to the right side. This scale right here should be level. So since they have to weigh the same on both sides, let's take a look at what the problem is here on our scale. We have spherical balls here that will say each weigh. Let's just say they each weigh 1 ounce. How about that? 1 ounce. So what that means is each of those balls weigh the same. We can even imagine them to be oranges. How about that? Oranges that weigh exactly the same. So each of those oranges weigh 1 ounce. So I have 3 oranges on this side, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 oranges on this other side. So let me just label that here. 10 on this side and 3 on this side. And remember, there's an equal sign in between them. So if we think to ourselves, we also see that the left side is not alone. There's also an X here. Remember, X means that it's a mystery number, right? We have this box on the left-hand side of the scale, and we don't know how much it weighs. We're like, hey, who put this here? How much does it weigh, right? But we do know when we put this mystery box along with 3 oranges, it equals the same weight as 10 oranges. So the equation would be x plus 3 equals 10. And you're probably thinking to yourself, I already know you're thinking to yourself, oh, I know what x equals to, right? Great. Awesome. But we're thinking about visual models here because as problems get more and more complicated, you may not be able to look at the problem and say, oh, I already know what x is, right? So we have to break it down and really look at the procedure so that when problems do get complicated, we can rely on our procedures and we can use our models to help us out. So going along with this idea that both sides have to weigh the same, let's pretend that we are trying to chip away and decide and try to figure out what x is equal to. If I were to try to figure out what x is equal to, I want to get x by itself so that I can then figure out how much it weighs. If x is still attached to these 3 oranges, it's not clear what x by itself weighs. So let me see if I could delete one of these here. Can I do that? Is it allowing me to do that? Take away one of those oranges, okay? Think to yourself, pause the video, think to yourself, what happens to my scale once I take away one orange on the left-hand side? What happens? Is it still going to be even-keeled? Is it still going to be exactly balanced? No, it's not, right? Because I've taken away 1 ounce on this side. So the scales are not going to be balanced anymore. This side is going to be heavier now, right? So this side is going to pull down. It's going to wobble, and this side is going to be heavier. So remember, we want the scale to weigh the same on both sides. There's an equal sign right here. So if I take away 1 orange on the left-hand side, I need to do the same on the right-hand side because it's a scale and I need both sides to be evenly distributed. So what I'm going to do now is I'm going to take away another on the right-hand side. So I've taken away 1 from the left-hand side and 1 on the right-hand side. So now they're equally balanced. So if you want to keep track with it on your paper, you can see that we have taken away 1 on this side and it wasn't balanced, right? So then we had to do the same on this side. So that's why we are left with x plus 2 oranges on that side, and now 9 oranges on this side, okay? So we have to do the same thing on both sides. If we take away 1 on the left side, we have to take away on the right side. So let's just keep going, right? But this time let's take away 2 on the left-hand side. So take away 1. Now I take away 2. So then it's lopsided again, right? So I have to do the same thing on both sides because I cannot just take away 2 here and not take away on the other side. I have to take away on the other side as well. So I'm going to go ahead and take away this one on the right-hand side. And in your notebook, you can just cross them out. I would suggest you cross them out rather than erasing them. Okay, so if you've erased them already, try to draw them back again and just cross them out so you can see in your notes later on that they were there, but you got rid of them. Okay, so we're going to cross them out. So we can do that in our algebraic expression as well, or equation, sorry. We subtracted 2 on both sides. That's why we are left with just x on the left-hand side. And we have 7 on the right-hand side. 1, 2, 3, 4, 5, 6, 7. That's how we know that x is equal to 7. Inside this mystery box, there are 7 oranges. Okay? Because we're doing the same thing to both sides. So, again, in your drawing, you had 3 originally on both sides, and what you did was you got rid of them. But the same amount on both sides. Okay, so your drawing in your notebook should look like that. And then you also might want to add a little note to yourself that we did the same thing on both sides. And you might want to write a note to yourself as well that you are doing the same thing on both sides because you want to keep the scale balanced. Okay? Do this. Do the same to both sides to keep the scale balanced. That's why we're doing it. Can't take away one orange from one side but not the other. Remember that equal sign acts like a scale. The equal sign says both sides have to be exactly the same. On a scale, that would mean they both have to weigh the same. Okay? So that's the scale model right there. So we showed you the scale model by drawing, and then we also showed you the algebraic model. So you could have just covered up the scale right here and just done it algebraically, and you don't even need the picture. This is really what you're doing. When you subtract 3 overall, right? In total, we subtracted 3 on the left-hand side. All you gotta do is subtract 3 on the right-hand side. This is really what you're doing, what's happening on the scale. But remember, math people, we're very lazy. So once we figure out the trick that you have to do both things or same things on both sides, we don't need to draw anymore, right? We can just do it algebraically and not have to draw. Let's move on to 2 other models. The 2 models are called the hanger model and the tape diagram. You should be pretty familiar with the tape diagram, but the hanger model is a little different, but it's very similar to the scale model. So what I want you to do now is to pause the video and jot down the hanger model and its example, as well as the tape diagram and its example. So here we are with the hanger model, and you notice it's very similar to the scale model. When I think about the hanger model, I'm kind of thinking about like a mobile, like when you were making a presentation in English class and you have to make a mobile, or if you have a clothing hanger, right? You can dangle strings from both sides, so it's like a hanger. So just like the scale, your hanger can be heavier on one side compared to the other. So it's definitely an easier way to draw the scale, because the scale is a little more difficult to draw. That took me a while to draw. Hanger model is just 2 sides hanging down. You will notice, just like with our scale model, we have numbers, which I made into oranges that weigh the same. And you also have a variable. Notice how we're drawing them differently. The variable I put as a box, and the regular constants, the fixed numbers, I put as circles. So same thing over here with the hanger model. We have the constants in boxes to show that they are the same. And then we have the variable with a triangle in there. Sometimes you'll see it with a pentagon or a hexagon, but a different shape and also a different color so that it jumps out at you that that's the variable and these are constants. So if you notice, this is the same problem as our scale problem. We have x and 3 on one side and we have 10 on the other. Do you think it matters that one's on the right side this time? The x and the 3 are on the right side this time and not on the left side? Yeah, it doesn't matter, right? Because as long as both sides are equal, it doesn't matter where I put one group versus the other. So here with the hanger model, let me get a lighter color actually. It's not a lighter color. That's better. with the hanger model, it's a little different in terms of how you can take away from both sides. So you would have to choose the side that has less in terms of the number. So this one is 3. So I can take away 3 on this side to make it equal to 0, and it disappears. And then if I do that on the right-hand side, I have to do the same thing on the left-hand side. So 10 minus 3 is 7 now. So now I have 7 remaining on the left-hand side and x remaining on the right-hand side. So then 7 would equal to x. Or you can flip it around, make it x is equal to 7. So what you're doing is you're trying to get rid of one side's number, choose the smaller side, so that goes bye-bye, doesn't exist. And then you're taking away, it's like you're cutting 3 away from the left-hand side so that it weighs a little less. Okay? So this is x equals 7. So this as an equation would have been written 10 equals, because remember the middle of the hanger is the equal sign, just like the scale, 10 equals x plus 3. This is x plus 3 because you're adding an extra weight to this side. And just like the scale model, we are subtracting 3 on both sides, getting rid of that smaller number, that weight that's attached to the x, so that x can be by itself, so x equals 7. And notice how I crossed it out because it's gone, just like over here. So that's the hanger model, very similar to the scale model. Tape diagram, on the other hand, very easy to draw. You guys have experience with tape diagrams, but the equal sign is a little different. Normally the equal sign is in the middle. Here we have the same exact problem again, but if you notice, instead of having different sides, we have different strips. So we have one strip that's equal to 10, just like how one side is equal to 10, and we have another strip that's equal to x and 3 combined. So here the equal sign is that they're equal in length. They should be the same length. Okay? So here is also 10 equal to x plus 3. So it's the length here that shows that they're equal. So the strips have equal lengths. That's what's a little bit different about the tape diagram. It doesn't have the balance thing that we were talking about before with our hanger and our scale. It's just talking about length. Okay? So same thing here. I want to get x by itself. X is attached to this 3, so I could get rid of this 3 here. If I do that, I also have to subtract 3 on this side to get 7. Because if I were to now change the length from here to now here, it's going to be shorter for both sides because I always want to maintain that the top strip is the same length as the bottom strip. The other way you can think about it is you can think about it as instead of that, you are now changing it, the top strip, to 7 plus 3, and the bottom strip stays as x plus 3. So if you have 7 plus 3 now, if you want to get rid of the 3, there we go, we get rid of that. Instead of 10, you've separated into 7 and 3, right? 7 and 3. So that if you are to get rid of the 3 over here, you also get rid of the 3 on top. So now x is equal to 7. They're equal in length. Okay, the other type of problem that you might encounter is a problem that doesn't have addition or subtraction. So the example I'm going to use is 6c equals 24. That's the same as 6 times c is equal to 24. Or there are 6 times that you see the variable c. There's a lot of c's. So here's the tape diagram and the hanger model for that same problem. 6 times c equals 24. On the tape diagram, you can easily see that 6c is equivalent to 24. The two tape diagrams are the same length. To solve this problem, you could, remember the goal is to figure out what c is equal to, one of the c's, right? So in order to figure out what one of the c's are equal to, you would just simply divide the 24 piece. Sorry, it's a little crooked, but you would take the 24 piece and divide it into the 6 different c proportions. 1, 2, 3, 4, 5, 6. So essentially what you're doing is you're taking 24, dividing it by 6. 24 divided by 6 is 4. So what that means is each of these c's is actually equal to the value of 4. So that 4 plus 4 is 8, 8 plus 4 is 12, 12 plus 4 is 16, 16 plus 4 is 20, and then 20 plus 4 is 24. So that's how you know that c equals 4. The way you would solve this algebraically, so without this tape diagram, is that you would see that 6 is being multiplied by c. So the opposite would be to divide. Multiplication and divisions are inverse operations. So remember, you're trying to get c by itself, so you're going to take both sides and divide it by 6. 6 divided by 6 cancels out to become 1. So 1c is left over on the left-hand side. 24 divided by 6 is 4. So 1c is equal to 4, or just c equals 4. In both cases, you are dividing, because if c is multiplied 6 times, to go backwards and figure out what each piece is tells you to divide. If you look at the hanger model, it's a little less obvious, because with your tape diagram, you can just line them up and divide, and you would see that each of the c's is equal to 4. With the hanger model, you kind of have to picture the actual situation of a scale. If I know that 6 c's are equivalent to 24, what I can do is I can imagine each of these c's, we're not actually going to do this, but we can imagine each of these c's grouped with a different value of its own, right? So then the question would be, how much would each of those c's have to equal to in order for all of the smaller blocks to add up to 24? So here we have 3, 4, 5, and 6. So what we did was we took each of the c's and we gave them a new little hanger. So here's a little hanger, that's this one, here's a little hanger, this one, here's a little hanger, this one, here's a little hanger, and here's a little hanger, and the last one has its own hanger. It has to balance out with 24. So what is the amount that would go into each of those hangers for each of the c's? Each of the c's would be equal to 4, let's say, ounces. So that in total, each of these c's added up together, 4 plus 4 plus 4 plus 4 plus 4 plus 4 would get it to 24. Another way that people solve it with the hanger method, because again, like I said, it's a little less obvious compared to the tape diagram. Tape diagram, you can just divide, is that people will see there's 6 c's, so they physically divide 2, 3, 4, and 5, they give each piece to each of these C's. So then they have to figure out, well, how much would each C get? And that would be 4 as well. So in both cases, it's 24 divided by 6 to figure out that each of the C's gets 4 to make up the 24. And remember, algebraically, you're just doing the inverse operation. Since 6 was multiplied by C, you're going to divide by 6 so that you get C by itself, and you get the 4 as well. Okay, so that's as difficult as it will get, but remember, you're doing the same thing on both sides, and you're doing the inverse, right? If it was addition, if it was something added on to your hanger or to your tape diagram, you're going to do the opposite so that you can figure out what the one variable is equal to. Okay? So let me know if you have any questions as you're working on this. Sending me a screenshot or the particular question is the most helpful. But good luck!